This conference will now be recorded.
Today we are going to have a look first at TensorFlow and Keras. Then we train some examples. After that, we go back to CNNs to see other stuffs. And then we have another example. So what is TensorFlow? So it's an open source library for numerical computation. It uses what we call data flow graphs. So nodes represent mathematical operations. So it represents your formula as nodes, which are mathematical operations like addition, multiplication, whatever. Edges represent data arrays, tensor. So it was developed by Google Brain, and it is easily integrated with Python, and it is really used by a large community. It is possible that it is like the top framework for doing deep learning right now. So first of all, you need to install it. You need to have a Python environment. For example, you can install Anaconda or whatever. Then on the command line, you can install TensorFlow GPU with this command line. If you are using Anaconda, you can use conda install TensorFlow GPU. If you want to use the GPU version, you need to have a CUDA-enabled GPU, like GeForce or this kind of GPUs. Or you can install it with pip install TensorFlow GPU. If you don't have such a GPU, you can use just TensorFlow. You can remove that minus GPU here, and you can just install TensorFlow. It will be a CPU version. But the CPU version will be a lot slower. The GPU one will, or you can use Colab, yeah, as Ali is saying. You can directly use Colab, and but it is limited, of course. You can't use it as much as you want. So Keras is also another library. So you have like TensorFlow is like a lower level library. It has all of these algorithms to do backpropagation, training, etc. And there are multiple libraries like TensorFlow, like CNTK, MXNet, Theano, and then we have on top of it Keras. Keras is like just another layer that simplifies how we use these frameworks like TensorFlow and the others. TensorFlow can be a little bit complicated to use, but Keras like provides us with a number of functions that are very easy to call. Here we can use TensorFlow, for example, with a GPU, with a CPU, or with a TPU. TPU is a tensor processing unit. It is generally right now developed mainly by Google. They have it internally. But for us, we use mainly, when you use it at home, you use it mainly a GPU or a CPU. One of them. The GPU is always a lot faster than a normal CPU, when we will tell why. Any questions so far? Any question? Yeah, a TPU is called a tensor processing unit. It's really close to what we call, it has a similar architecture to what we call an FPGA. So it is a circuit that does training like, how to call that? It doesn't have like something, a controlling unit like a CPU or a GPU. It is just like a circuit, and things will flash in that circuit, and it will be one batch, or one epoch being trained in one go, in one like a cycle clock. It's very close to the FPGA architecture. This is the tensor processing unit. I think, Yunus, you are familiar with that. As your background is close to these things. So Keras, it makes using the underlying framework a lot easier. Creating and training a model is just a few lines of codes, as we are going to see. Now it is part of TensorFlow. When you install TensorFlow, you get Keras along it. This is version 1.4. Some of the contributors to Keras, not only those guys, we have other contributors as well, but the main ones are these guys: Microsoft, NVIDIA, Google, AWS. We don't see Facebook, one of the big contributors on AI, because they have their own library called PyTorch. They have Coffee as well, but PyTorch is used a lot. It's probably the second most used framework for deep learning. So to use Keras, we have what we call a sequential model. Sequential models are what we use most of the time. Like 70% of the use cases are sequential models. What are sequential models? Are just simple stuff. Layers are stacked sequentially. Like you have a CNN layer, a convnet layer, then a fully connected layer, etc. Like we have one layer next to each other. So far, we have seen only sequential models, whether in a feed-forward neural network or a convolutional neural network. And then you've got an output. This is the code on how to use Keras, a simple code. So we call the sequential, we initialize it with sequential. Then we add a first layer. This is a conv2D layer, convolutional layer, with 64 filters and 3x3 kernels. It has an activation function rule. It is something like that. 64 filters. What does 64 filters mean? If you remember from last time. What does 64 filters mean?
The input?
Not the input, no. The input is, no, it's not. The input shape comes from here.
Okay. Yeah.
It is how many
bytes.
Sorry, what?
Hidden layer.
The number of
Hidden
filters
layer?
is simply, as if you remember last time, well, they are always hidden layers here.
The number of filters.
It's simply, sorry, what do you say?
Number of filters?
Of what?
Filters.
Filters, yeah, filters, exactly.
Yes.
Is the number of filters that we are going to have. It means that each filter, what does each filter do? What does each filter do, guys? Each one of them is going to learn a particular shape. This shape is 3x3, something like that, 3x3. And each filter is going to learn a particular shape. For example, a line like that or a line like that. So this filter is capable of learning one of the shapes, one of a basic shape. So we've got here 64 shapes that we are able to learn. 64. So you've got, you can say we've got 64 neurons. 64 virtual neurons. They will slide along the image. If you remember from last time, we said a neuron would slide. It has a kernel of 3x3, because we said here 3x3, kernel of 3x3, and it will convolve. What is convolving? What is convolving here? Don't be shy. Speak, please. Tell me what is convolving here. In our case, we have a virtual neuron. We call it virtual for a reason that I'm going to explain. But what?
Is it training one neuron?
Convolving is simply sliding. If you remember, we have this image. This neuron is connected to 3x3. So it will need to slide along the image to scan it like. And it will look for a particular shape. For example, if you are looking for a shape like this, it will look how close, for example, here, this 3x3 to this shape. Then slide a little bit, depending on how much we want to slide. The stride, we call it the stride. We move by one, and we look at this 3x3 again. So it's like sliding, it's like scanning. Do you remember, guys, from last session?
Yes, yeah, we do.
Perfect. So this neuron will slide here, looking for a particular shape that this neuron is specialized on. Training will tell it what to look for. When we train, this neuron will start looking. So each neuron will probably look for a different shape. This one will look for this, this one for this one for something maybe like this, etc. And because it will slide, Normally, a single neuron has multiple inputs, a regular neuron that we know. And how many outputs does it have?
One.
Just one, yeah. No, a regular neuron has multiple inputs and one output. Here we have multiple inputs, like 9, if it's 3 by 3, but we will have multiple outputs. That's why we call it a virtual neuron. We have multiple outputs because it's sliding. So for each step, when we are sliding, we get an output. And this is called a filter. It's the output for each neuron. So this is a filter. Or the result, which is the activation map. So the activation map is the output of each neuron. For each neuron, we get one map. So for this one, so here we are looking for 64, which means what? It means what? We have 64 basic shapes, like this one. Maybe then we have another one like this. Maybe we have something like this. Maybe we'll have like this. And they are determined also, of course, by backpropagation and the gradient descent shapes. Then it is connected to same again. This layer, these ones are connected to something similar, to 64 neurons. And these neurons will look at what basic shapes we have. And we have also 64 other filters or activation maps. So these filters will contain what? Will be special, or this neuron are specialized on what?
More complex.
Exactly. Thank you. More complex shapes. So here we get, if these shapes are present, then here we get more complex shapes that are combinations of these shapes. It can be a square, circle, triangle maybe, and so on. And then we got another 64, 3 by 3 again. So it's also focusing on 3 by 3, just a small region. And this is again more complex. Then we have a dropout, a max pooling. What does the max pooling do? This is just a revision from last time. I'm trying like just to make sure you remember the important concepts. What does the max pooling do?
Reduce the dimension.
Exactly. Thank you.
Picture.
It reduces the dimension. So this is one of the feature maps like this. A max pooling of 2 by 2 will reduce the dimension. I think we need to revise a little bit this stuffs. It will reduce the dimensions. For example, it takes every four values and transform them to 1. It takes only the maximum. So if we have here 4 values, 3, 5, 1, 0, it takes the max pooling will take only 5.
Reza?
Yeah?
I know the pooling, what does it mean, but always I have this question, what is the difference between the filter and the pooling?
Well, the filter is looking for a shape. The filter
No,
has
I mean
learned the
the
shape.
operation itself. We do like a batch of 3 or 3 column and 3 lines, and then we represent it by only one pixel or one number.
I don't think I understood your question. What one number
Yeah,
are you talking about?
for example, a pooling, we use the matrix of, for example, 2 column and 2 lines.
For
and
pooling,
then
yeah. But this is for after the result. After we got the result.
One number.
After the last result. Well, we have multiple filters. Each filter is a 2D matrix. This one, like, this is also a 2D matrix like this. So this is one activation map. For example, this one or this one. And then we start pooling. Pooling, every 4 values will be converted into 1 value, taking the maximum. Like
this principle, we use it even in the filter.
No, that's not what we use in the filter.
In the filter, we use a mask.
In the filter, we convolve, we slide. It's not exactly that. We slide. We have spoken about it the last time. So what we do in the filter is that we slide. Here we have one value. But when we move here, we move next to it. We are not jumping 3 by 3. We are not going here generally when you use a slide of 1. We are not going to here. We are moving only by 1. So we're not reducing. We are not reducing this 3 only to 1. We are moving only by 1. We get almost the same size of the matrix, almost. But this one, the max pooling, will reduce it directly.
Okay.
We are looking for a particular shape, but we use a stride of 1, what we generally use, we are moving only by 1 pixel. So this zone and this zone are overlapping. So we're not reducing the dimension. It might be reduced, but by very little. Okay. I will revise it after the example. I will go back to it and try to revise it again, because we did this part last time, but I think you were not here. So, are you happy with my answer, Najwa?
Yeah, I got you. Yeah.
So here we are not reducing the dimension of the dimension. Here we are reducing, and we are reducing it because when we have, like, for example, 5 here, is 3 here, it's a 0. We try to how to explain it. If in an image, because these guys are overlapping. This is the output from the same neuron when we are convolving, but they overlap on the pixels. Yes or no? Because we are convolving. So those that are close to each other, so this one and this one and this one and this one, when we go down, they are overlapping. Yes or no?
Yes.
They share a lot of pixels together. So if this shape, for example, if this neuron is looking for a shape like this, it is looking at it in the beginning from this, focusing on it on here, all of this, and then it moves just a little bit. But it is basically the same shape when we convolve. If you look at it, for example, in the beginning like this, after, when we convolve, you look at it like this. You move just a little bit, but it's basically the same shape. So we take the maximum to say that in this zone we have this shape. This is like a simple explanation. We take the maximum because this will be the maximum value, because it looks like this shape a lot. When we move a little bit, we lost just slightly. We lost this zone. So if we take the maximum, it will just mean that in this zone we have this shape, and we don't care about those that are overlapping with it and looks a little bit less like it, but very close to it. Okay? Does it explain? Is it clear why we use the max pooling?
Mm-hmm.
And it can help
Yes,
a little bit with generalization. It makes things more general.
Yes.
Mm-hmm. Sorry, I don't really have time to go back to all of these concepts. I will invite you to have a look again at the video from last time.
Hi, Rida, do you hear me now?
Yeah, I can hear you.
Okay, cool. So just question here for the max pool 2D. Is it why it's the size is 2 by 2, not 5 by 5 or 4 by 4?
Yeah, we generally use 2 by 2, but we are not obliged to use more. Well, the more you use, the more risk you get to lose some information. So we need to pick the right number. 2 by 2 seems to be good in practice, but you can use more.
Okay.
If you use, for example, 10 by 10, maybe things are not really overlapping. So you are taking two numbers or the same shape are present twice, and they are not overlapping, and we are reducing it only to one value. So we are losing information. We start losing a lot. So it's good to have a good number. 2 by 2 seems to be safe and acceptable.
So do you mean by 2 by 2 is the best option here?
In many cases, I can't guarantee that it is the best option everywhere, but it is a good approximation for most cases.
Okay, thank you.
Thanks. So here we are stacking. You can see that to create a convolutional layer like this one, it's just one line of code. Very simple with Keras. Then another one, then a max pooling, another one. You can put any architecture you want. A max pooling. And the dropout, we are going to see, well, we talked about it a few during past sessions, but we are going to see the effect of dropout. Then flatten is just, here we have what are the shape of the data at this output after this max pooling? What will be the shape of the output? Something like that. Sorry, my drawing is a bit horrible. So the output will be something like that. Yes or no? Do you agree with it? The number of feature maps and the size of the matrix after the max pooling, the last max pooling. So we got something like that. At the end of CNNs, we always use a dense layer, which is a normal feed-forward neural network. We always use that most of the time. So what we do is flattening. Flatten, it just transforms this tensor, it's a 3D matrix, to a one-dimensional array. That's all what it does. So each one will be in, so here we have this value, a lot of values. Each one of them will go to a place, etc. Because a dense layer is connected to something that is linear, to a vector, not to something that is like that. This just transforms it from a 3D tensor to a 1D array. Then we connect it to a dense layer. This dense layer is taking what? It's taking all the features that are in my image. What kind of complex shapes, of course. These are like basic shapes, and then the more we go up, the higher in complexity we go. So it's taken like more complex shapes like eye, mouth, or ear, with all of this. So things that are a lot more complex. It's looking at them and making a decision. So we have two dense layers, one 128 and one dense layer with a number of classes. So if we have 10 classes, so we will have 10 neurons. Each neuron will output the probability that a particular class is the right one, whether it's dog, cat, etc. The softmax activation, why we use softmax. Can someone tell me why we use softmax?
Multi-class.
Sorry, what?
Multi-class classification.
Yeah, but what it does, what does the sigmoid do?
Sigmoid high probability.
It transforms an output. So if we have a value here, it transforms it into something between what? 0 and 1.
And 1.
This is what the sigmoid do. The softmax
-1 to 1.
But here, how many neurons do we have at the last layer? How many neurons?
Any classes.
How many?
As n class.
Yeah,
number class. Yes.
Exactly, n class. The last layer is n class. The softmax, what it does, it transforms the values that we get out of here into a probability where every probability in each class sums up to 1. So the sum of the probabilities of the values will always be 1. Sorry? I couldn't hear you. The sum of the probabilities. So after, for example, if you get an image, you pass it through this neural network. At the end, you get, if for example we have 10, the number of classes is 10, you get a vector of dimension 10 And here you will have probabilities. The sum of these probabilities will be 1. And of course, we generally just take the highest probability. For example, if this is cat, dog, so if the cat probability is 0.6 and all the others are low, so this is probably a cat. Can someone please, I can hear some background noise. Can you mute on your sound? Okay. Guys, please, I'm hearing a lot of background noise, so
I think, Rita, you have the right to mute everyone.
yeah, I don't want to use it, but yeah, if the person is not here, I have to.
Reda,
Yeah.
please, how we can use the good architecture for our problems?
The good what? Architecture. Yeah, there is no direct answer.
Rule.
There is no easy rule. You have to try.
Okay.
You have to try different architectures, different optimizers. There is, and you, with some experience, you will be able to tell. Some, of course, if you have an image with a lot of complex shapes, like faces, etc., you will probably need something very deep. If you have an image with very basic shapes, like for example, cells are a lot simpler than faces, for example. And so you can go with not a deep layer, deep architecture. And we have architectures that have proven to work in multiple cases. So you can always reuse them. And we are going to see that today.
Okay, thanks.
Okay. So what is good about softmax? It transforms the output into probabilities. And you just take the maximum to understand. That's the maximum to understand which one is, like, what's the highest probability. Because a neural network will output any number, not just probabilities. So the softmax will transform all these the values of the output into probabilities. I want to just to revise all of these stuffs from last time. I know it's not easy to remember everything. There are also more advanced ways to use keras. For example, you want to subclass. For example, you have a model or that you can inherit from, or you can create your own model as a class. Instead of here, it's just an object that we are adding things on it. But here you can create a class that represents a model. And inside in the init, we can define the model. This is more cleaner. And then in the call, we tell it how to compute things. So we are not stuck in them. We just define them. And then when you use the call with an input, after each, when we put an input here, we get a result, and we put it here, and this is the result, and then we get it again here, and we return it, because here we have just 3 layers. If you can see it, we are not stuck in them, but we are explicitly calling each layer, getting the output, and the output of this layer is going again here as an input here. This is the output, and until we get the last output of the last layer. And here you can see it's cleaner. You can put it in a file name, and you can call it like that, and just call it fit with the input and the labels, and we start learning. This is just a more cleaner way of doing things. So this is, you can also create custom layers, like custom loss functions with keras, custom activation functions. Well, it is not very easy, but you can always do that. Okay. We need also some titles to provide the derivatives if you want some custom loss function that don't exist in keras already, or some activation function that don't exist as well. But if you use combination of activation functions or combination of loss functions, you won't need to provide the derivatives. But these are more advanced stuffs. So this is for Keras. Also, we have here how to run an example. So you just install, especially the example that I'm going to use with you today. So you just install Anaconda, like I said in the first slides, install TensorFlow, and then open Jupyter Notebook via, you just, it is in the directory of Anaconda. You can just launch it. Once it is launched, you get the interface. You can open any notebook and execute it. Very easy. Okay. So let's go directly to the practice, and then we come back to the theory. Any question, guys? Someone wanted to say something? Oh, so Ali, you said, what's the difference between average or max pooling? Yeah, some people prefer to use max pooling. Some other people prefer to use average pooling. And it really, I think it depends on your case. In some cases, you might prefer to use average pooling. In other cases, you might prefer to use max pooling. It's up to you. I don't know explicitly what cases are best for average or what cases are best for max.
So we read that we take only one value in both. So for max pooling, we take the maximum, and for the average, we just calculate the average and take it.
Exactly, yeah. That's true. Also, you said, how do you know the size? Yeah, you already asked that. Yeah. So let's now go here and try some practice. So mnist, this is a very simple data set that you can get here. So it is already part of Keras. You don't even need to download it separately. It exists inside Keras because, like, every example is using mnist. Mnist is just simply a matrix of the size 20 by 25 by 25, and it is numbers. It is simply numbers, handwritten, as you can see. So this call will just download the data set, and it is already divided. It is a data set where we have the training set and the testing set. They are divided inside. Okay, so let's execute it. Let's get to that to see the drawing. So training is 60,000 examples, which is not bad, and the size is already 28 by 28. And these are the labels. Of course, for each example, we have a label. And then for testing, we have 10,000 examples, 28 by 28. Same of the number of labels for testing. This is an example of 25 or 20 images from the data set. We have 10,000, 60,000. We can plot them all, but these are few examples. So here, what we are going to do is to prepare the data. Well, we already did that, including the data set. Number of classes. So this is to see how many classes do we have. So this is the size. Len in Python is the size. Unique. Y train. What does it mean, guys? It's very simple. Y train are the labels. If it is 1, if it is 2, 3, etc. Unique is a function in NumPy. And what it does, it tries to see how many unique value do we have. How many classes are we going to have here, guys?
Can you go back to the picture and we can tell you?
But how many do you think? It's images of numbers.
Yeah, is it all of them?
Yeah.
20.
20 numbers? 20 distinct numbers, do you think?
10? 10?
Yeah, just 10. From 0 to 9. It's digits.
Oh,
yeah. Yes.
From 0 to 9. We are dealing with digits here. So unique white chain are the labels, all our labels. So when we look at how many unique labels do you have, you probably get 10. So you get all of them here, and the len is the dimension of this vector. That is 10. From 0 to here, we have the value. Shape 28 by 28, and number of classes that we are printing here. Number of classes, and class, we are printing this. It is 10. Well, this is for data preparation, or we reshape the data. Shape 0, shape 1, and shape 2, and we add another dimension. It's because a matrix is only an in this image, because they are black and white. They are only 2 dimensions, in 2-dimension space, black and white, and we have only one value. It's not an RGB. So here we are converting it into 3D, but not a real 3D. We just, sorry, it's two dimensions, each image, because we have only one value. It's a grayscale, not RGB. So when we convert it into something 3D, this becomes like this. It's still, we have only one value here. We have only one value here, but it's like a cube. It's because CNN's convolutional network takes data from that into that shape. They are the same, exactly the same values. But this is a 3D representation, where here we have only one along this axis, one value. So this and this are the same, but they are coded into like 3D here and here into 2D. But the third dimension here is only one. Is that clear? Why we are doing this reshape? There's a channel dimension. If we had RGB, if we had an RGB, we will have how many here? We'll have something
3.
like that. Exactly. We'll have something like this. We will have 3 values here. So here we have 3 values. So this is the image, and this is R, G, and B. So a value per channel. Okay, so far? It's just to prepare the data to transform that into something 3D. This is the shape of the image. How it is 28 by 28 by 1. 1, like I said, it's 1 dimension into the third dimension. Number of classes. Now we build a model. This is a very simple model. It's simply one convnet. How many basic shape do we have on it? On this convnet? Tell me what this represents. Tell me, guys.
32.
32 what? What is 32? Yeah, this is 32 filters, and it produces 32 feature maps. 3 by 3 is what? Tell me, guys, 3 by 3 is what?
Is the matrix of our value.
It's the kernel, yeah, the thing that is going to slide. The thing that will slide along the image to get my values. There's the kernel size. Activation rule, if you remember it. What is it? Activation rule. It takes something. It's the activation function, yeah. It's the sigmoid is like that. The rulu is like that. The rulu, if it is negative, it makes it 0. If it is positive, it keeps it as it is. So it has like a better gradient than the sigmoid. The sigmoid is always 0 or 1, but here the gradient will be a lot better. So we use the rulu generally in deep networks, which keeps us to would help us to have like a faster training, and we can go very deep. Kernel initializer is just how we initialize the weights in the beginning, the weights of my network. And this is just the input shape, how the input is encoded, which is this value, 28 by 28.
Rida, excuse me. Rida, we are talking about input shape. So there we will put our image, for example.
Sorry, could you repeat, please? Could you repeat, please?
In this parameters, input shape, in this parameter we put our data, the image.
No, not the data yet. Not yet of the data. This is just how the data looks like, the shape of every image, which is 28 by 28 by 1.
Okay.
It is not the data yet. We are just saying how the data will look like. That's all. We needed to prepare my network. We know how many weights we need, because the weights depend on the shape of the data.
Okay, so where we can put our data, I mean images, in this model, in the training.
It's here. It's coming. It's coming. Don't worry.
Okay.
It is coming. Here we are just shaping the network. We are just putting the structure of my network.
Just a model, creating a model. Okay.
Exactly. We are creating not even the model. We are creating the structure of the model, preparing the weights, etc. in memory. Then we flatten after every convolutional layer. After putting all the conv layers, we flatten them. Flatten them means we transform them. Here we get a tensor, a 3D matrix, and we transform it into one array. Then we put a dense layer of 128. This is the decision. We call them the decision layer. A dense layer, a dropout. What does the dropout do, guys? If you remember.
Just keeping 14% of data.
Sorry, what?
Of neurons. Keep it for keeping just 14% of neurons.
Exactly. No? At each iteration, each epoch, we keep only 40% of the neurons and we discard the others randomly. When you remove certain neurons randomly, it's like what effects do we have when we use the dropout? If you remember, it's like
make the algorithm quicker, kind of reducing number.
No, not really. It's not going to be quicker. It's going, in fact, to be slower. The algorithm itself, but it's like creating multiple neural networks and averaging them. If you remember this dropout, what it does, it's when you remove, and I will send you also the slides, and I will invite you to have a look again. When you remove certain neurons randomly, it's like at each iteration, each epoch, we have a different architecture. It's like we are trying to optimize different neural networks and then averaging them.
So for having good performance.
Exactly. Overfitting will be reduced, and we are going to see that. Overfitting will be reduced. This is what dropout does. It really helps a lot to reduce overfitting. I will send you the slide again, and we've done a good part for this dropout.
Yes, Rita, just excuse me about dense. What's the role of dense?
Dense layer is a regular neural network. The dense layer is going to look at all the features that my convolutional neural network has produced. My convolutional layer has produced to determine what person it is on a picture. We need to look at everything. So this is a regular neural network, not a convolutional neural network. Dense layer. It's like something like this. Connected to all, each neuron is connected to all the outputs. And same for here. It's not the convolutional neurons. And so it looks at all the features and make a decision. Then here we have like 10 neurons connected also to all. And here we get the decisions. And here we got a softmax. The values here will sum up to 1. So it's a vector of probabilities. Okay? Are you happy with this?
Yes, thanks.
I'm worried that nobody said no. Are you all really happy, guys? Who is not happy? I will give you a gift if you're not happy. I'm just kidding here, but
I'm not happy.
but why are you letting me moving forward?
I get the dropout. I get I forgot the rule. I don't know what you've done in there.
Yeah, let's repeat it with the rule.
Yeah, thank you.
When we got this kind of neuron connected to a 3x3 kernel, this is just a portion of the image. So this neuron will output a value. For example, let's say a 10. Normally, in normal circumstances, if we use the sigmoid, it will tell us, and this neuron is looking, say, for this shape. It will tell us a sigmoid how close this drawing here is to this shape. It will be like a 0 or 1. It can be in between, but basically a 0 or 1. The sigmoid is shaped like that. So it tells us if it is like that, it will probably be a 1. If it is something, for example, like that, it can be a 0, but because this one is very far from this. Are you happy with this, Emma?
Yes, yeah.
But why do we prefer the Rulu instead of the sigmoid? The Rulu doesn't tell us only if it is present or not. It tells us how much it is present. It tells us how much it is present. It's a value. So if it is a 0, it's a or negative. This is the Rulu, the shape of the Rulu. If it is negative, it becomes 0. If it is positive, it stays as it is. So a negative value doesn't mean a lot. It means that the shape here is very far from the shape that we have in here. A negative value. It's completely the opposite. But a positive value, it tells us how close this shape is to this one. So if, for example, here we have this, and in this portion of the image, we get something like this. This is very close to this. So we get a high value here. If it is exactly the same, we got even a higher value. So this is what the Rulu can do. Although the sigmoid can do it, but to a lesser degree. And also, the Rulu has a better gradient. Another thing. The sigmoid here doesn't have always a good gradient. The Rulu here, if we plot the loss function, the sigmoid, I think the loss function for sigmoid would be something like that. So here and here, we don't have a lot of gradient. But the Rulu here has a very nice gradient, as you can see. So we will converge faster with a better gradient. When you get to here, the gradient is almost close to 0 for this loss. But here, it's always not like far from 0. And it can give us a better optimization. Are you happy, Amal, with the Rulu?
Yes, yeah, I remember now. So so when we have like a high value, it means the neuron is more likely like to be close to the shape that we're looking at.
Yes, we get values that are not bounded, but we get as close. If they are close, we get very high values.
Nice, okay. Thank you. Yeah, thank you.
Are you happy now?
Yes, yeah.
The softmax is fine for you guys?
Yes.
Perfect. So we now know what is this 32. We know what is this kernel size, the Rulu, input shape, which is just basic information about the network. Here we have a dense layer. The dense layer is connected to all the input, unlike the conv layer, that is where each neuron is connected to only a portion of the input. So here we are looking at all the features. Then a dropout. The dropout is like an ensemble learning. It's like we are training multiple neural networks and averaging them. If you remember, when we did the random forest, we trained multiple decision trees and they voted. And we said that this will produce a better performance for the model. Overfitting was reduced by a good value, if you remember. Do you remember it?
Yes, yeah, it reminds of it really. It's like, okay. Yeah.
Great. So here, but here in neural networks, we cannot make a lot of networks and then make them voting. Why? Why? We said we can't do that. Why? We could, in theory, produce like multiple neural networks with different architectures, and at the end they will vote. We take each one, like we have multiple, let's say we have 100 neural networks. Each one will produce something. It will say a cat, a dog, each one will say something, and then we can vote. But we said that this is not practical. Why? Why? Why do you think it is not? Tell me.
It takes too long?
It takes too long, yes, exactly. Training a neural network is a very heavy process. And if we are going to create 100 neural networks, it will take us a lot of time and a lot of resources. So what we do instead, this is the magic bean, the dropout. The guy who produced it was probably a genius. By simply putting this probability, and in each iteration, we remove some neurons from the network, we get a different architecture each time. And then we average at the end, we almost like we average them, average like the weights of every neuron that we got for each iteration. And by that, the effect is exactly like we are training multiple neural networks and averaging them. And it generally makes the time like double or something like that. But the overfitting is reduced. The model can generate a lot better. Okay? I think I have given you a graph about the loss with dropout and without. And we are going to see the effect today. So this is a very simple neural network, a very simple convolutional neural network with one conv layer, one first dense layer, and one last small, what we call output layer. Then we are going to use the optimizer, model compile, and we give it the optimizer, Adam. You remember we did some optimizers. Can you tell me some of them? You remember some of them? What we did? The first one?
Momentum.
Yeah. MSE is a loss function. It's not an optimizer. And we use it in regression. We use the momentum. They are all basically stochastic gradient descent, SGD algorithms. So we use first the momentum. We said that the momentum can converge in a quicker way. Then we had a look at RMS.
Prop.
RMS prop, exactly. And then Adam was a combination of RMS prop and momentum. Momentum takes the path gradient into consideration. RMS prop changed the learning rate. Try to change the learning rate. And Adam combined both of them. We are using default parameters, which are this. The parameters for Adam are this: the learning rate, the beta, which is, I think, the coefficient for the momentum. If you look at the formulas, we have the coefficient of the momentum and the coefficient for what we call that came from RMS prop. Epsilon is just a small value when it is like close to when we consider it as 0. RMS grad, I think I don't even remember what it means. Sorry. So this is Adam optimizer, and here we are training. Mahdiya, this is where we train. When we call the model to train, we give it the data: X train, which is the input, the labels Y train, the number of epochs. Here we said we want 20 epochs. The batch size. The batch size in each iteration here we are going to use 256 batches. 256 the data points. This is, we said, part of the stochastic gradient descent. Stochastic gradient descent doesn't choose all the data at once, but instead At each step, we use 256 randomly selected data points.
And epoch is the number of iterations?
Yes, here we have 20 epochs, as you can see here. So let's start the training.
Is it, sorry, Rada, is it always 256?
No, you can choose this number. It is really a tricky number because it depends on your hardware. If I put, for example, a very big number here, my model will crash because my GPU cannot contain everything, for example. So you have, it's good to have a big value. It can speed up operation, the learning, but we are constrained by hardware. And sometimes, like a lot values that are too big are not always good. They cannot speed up. Like we need to find the sweet spot for the batch size, and then of course for the data set. And these are the validation data. I want to see the accuracy after each training. So after completing the training, doing a number of epochs, doing like a number of steps, here we get some accuracy value. So here we will get the accuracy for training, and here we will get the accuracy for testing. Let's start the training. Oh, sorry, what did we have? I did not import sequential. It's weird. Second, I think I'm missing an import. No, I have it here. Maybe I didn't execute this one. Yeah. And let's start the training. You can see the accuracy for training here, and the accuracy for testing is here. It's even higher, which is weird for now. The accuracy for testing is higher than the accuracy for training, but they will get very close quickly. How far are we? 98%, which is not bad. 98.5. You can see this is improving, but this is not a lot improving. Yeah.
Rita, this training is this run for test and training.
We are doing the training at the end of the iteration. We are doing the testing to see how it is improving.
For each epoch.
Yeah, we are doing that for each epoch. We are not obliged to do that, but just for the purpose of seeing how testing is improving. Okay.
We can do the training first, and then after we talk about.
Yeah, you can do it only once at the end. Yeah, generally we do it only once at the end. But here I wanted like to see how the accuracy on testing is evolving.
Okay.
So here we got at the end 98.71%, correct? And accuracy on training, of course, it is like about 1% higher. The score is not too bad. What do you think? It's like 98.71% on testing. These were not used for training. These 10,000 cases, these 10,000 ones for testing. And they were like the data set or the model has never seen them before. It's just seeing them for predicting. And we are getting 98.71%. This is an acceptable score, more or less. Okay, guys?
Yes.
Let's now try a more complex model like this one. So it is containing 3 conv layers, then a dropout, a little bit of dropout. You know, with conv layers, we use only a little bit of dropout. We don't use a lot. Then another max pool and max pooling, sorry. Here we didn't even use any max pooling, I believe, because it has only 1 layer. It was very small. A max pooling, then another 3 conv layers, a max pooling, another dropout, flatten to make it just one vector, then a regular dense layer and another dense layer with n classes. So this is more complex, and we have a little bit of dropout here and here. Let's see, we have 30 epochs. It will be slower because we have a lot more ways to train now, unlike the previous case. Let's try. You can see it's slower. Here we can see the number of weights I executed previously. So the number of weights for this network is 1,600,000 or 700,000. These are the number of parameters for this, and this is not big at all. This is considered as a very small network, a very small architecture, and you can see it has already 1,700,000 weights. So how much we got better than the previous architecture in the first epoch? You can see that. It's the same data set, same configuration. We got already 98.79% on the first epoch only. Here at the end, we got 98.7, so it's almost the same. Let's see how far we can go. Feel free to ask me any question, guys. It will take some time, maybe a few minutes.
Yes, Reda, please, if we want to keep the weight matrix, for example, in which layer we can find it?
You want to save your weights?
Yes.
Yes, it's just a few lines of code, a couple of lines, that's all. So this model, you will save it into a file. You will serialize it and you store it on your hard drive, and when you load it, you just give it the file name and it will be loaded again. It's like just a couple of lines of code. I can send them to you, or you can find them on the internet. It's very simple.
So this is for saving the model, but I'm talking about weights.
The model and the weights, not just the model, of course.
Okay.
Fit.
So if I want just the weight, it doesn't possible.
It is possible to separate them, to save the model like separately and the weight separately. It is possible to do that as well. Okay. You can see here third epoch, and we are already at 99.30. That's third epoch. We are beating 20 epochs here. That's nice. On testing, of course.
Yeah. What about training, Reda?
What do you mean by training?
The accuracy.
Yeah, here. This one.
Yeah.
Yeah, it is improving a little bit, because what the gradient descent is using is optimizing this accuracy. Well, it's actually optimizing the loss function. This is the main thing to optimize. But when this reduced, this will get higher. So this is getting reduced, the loss function, and the accuracy on training, it is getting higher. At some point, because the accuracy on the training sample is a lot bigger than the testing sample, so we will generally get less accuracy in the beginning. But after that, it will overtake.
Slower. Yeah, it would be slower than
this will improve further, and this will improve like in slower way. So this will overtake it and will get a higher accuracy here, almost 100%. And here it will struggle a little bit. Let's see, continue how it is improving. You can see with this architecture and by putting some dropout here and here, we got a lot better. Well, not a lot better, but better. I can try also to remove the dropout here in the previous example, and you can see what will happen without the dropout. Unfortunately, I can't use two models at the same time, because the model, my GPU is almost already like consumed by one single model. It's a 4 gig GPU, and it's already consumed. And this is a very small model, by the way. It's considered a small one. It is almost entirely consumed by this architecture with weights, this 1 million weights, and the dataset or the batch dataset, because it's stored in the GPU as well. So you can see here, we went a lot far, 99.4.
Reda,
Yeah.
I have a question. When you are working and you're running like a model like this, so do you wait for the results, or you just keep watching like this?
It depends. Well, if you need quick answers, or your model is not going to take more than a few minutes, you can wait. But generally, no, we don't wait if it is taken. I had models.
Do you drink tea? Do you drink tea while the model is running?
You go home, you come back. It happened to me like somewhat. I have trained models with 12 hours and with 8 GPUs at the same time working.
Sorry, how many hours?
12 hours using 8 GPUs. And I just stopped it. I could have done. Sometimes it can take a week or so. So yeah, you launch it and you forget about it. And this is with like machines that cost like $100,000. It's not like my poor machine right now struggling.
No, it's really close. The accuracy for both.
Yeah, for both are close. This one will probably overtake it, but this one is really nice. I think the state of the art, the best score for mnist is 99.7 or 0.8 that I have seen so far. So as an exercise, guys, I will ask you to beat at least this score. I will give you this file, and I want you to beat this score. It's not the best score. It's just an architecture that I put myself without a lot of thoughts. I tried a few architectures. And I got this number, 98. I think my best is 99.6. So I want you to beat that, or to get maybe the best possible score. That is 98.8, or at least very close. That would be nice if you want to do it. So these are the numbers of weights that we are training.
Reda, is the accuracy for testing fluctuating, or is it just me?
Of course, it will fluctuate a little bit. It is fluctuating a little bit. This will fluctuate less, as you can see.
Yeah.
Because it is related to the loss. But the optimizer, Adam, is trying to bring the loss to 0. And the accuracy on training is always related to this loss. So this is like more stable.
It's increasing, like, it's constantly increasing.
But this one, because the model doesn't even look at it while training, it's like it is the exam actually for the model. So of course, the results on the exam will not always depend on how much you study. You've got there is luck inside. There is also other things. Does it make sense for you?
Yes. Yeah. Okay.
And these are the numbers of parameters per layer. So the first layer has 640. Sorry. Then it has a bit more, the number of parameters. Then the dropout, of course, doesn't have any parameters. You just reducing the feature maps. Same with the max pooling. Then the conv2d, the other conv, they have a lot more. Then max pooling dropout, they have nothing. Then the first dense layer has a lot because it's connected to every output from the previous layers. So it has like over 500,000 parameters. Then the last one doesn't have a lot because it's just 10 neurons connected to all the outputs again to the previous layer. And these are how.
Sorry, Reda, why it reduced between the
is the number of weights. Why this reduced was reduced?
Yes,
because,
dense 2 and dense 3.
Because
yeah.
it's 10 layers. This is 128 neurons, all connected to a number of outputs. The number of outputs here is not this. This is the number of weights. The number of outputs depends on the numbers of this 128 filters and how much the convolution do we have. So we slide over them. So we get a number of outputs, and they are multiplied by the number of neurons here. 128. So the number, I don't know how many outputs do we have here. I don't know how to. You can probably find out by some way. And they are multiplied by 128, so we get this. And then we have a number. Again, 128 outputs here. So each neuron here is going to have 128, and they are multiplied by 10. But we have a bias, so it is +1. They are multiplied by 10, which means 129, 0. Because the dense layer, each neuron produces only one output in the dense layer, unlike the conv layer.
Yes.
So only every neuron produces one output, and each neuron of the 10 neurons on the last layer, we have 10 neurons, so each one connected to 128 outputs. So the weights are multiplied. Each output or input here has a weight plus the bias. So we have 128 weights plus the bias, so 129. So here and here, 10 times 129. So we get 1,290 weights in the last layer. Is it fine?
Yes, yeah, thank you.
Yeah. But here we need to know this to make sure we know this. It depends on the number of outputs. So it's how we are sliding and these computations. Next time we are going to see how to compute the number of weights, total weights, etc. Where are we? 18. Sorry guys, it's a bit slow. It's a bit too 60% of what we want. After this, we are going to look at fashion. It's a more complex data set. It's where it's like still grayscale, but we have cloths instead of numbers. It is a score here there in fashion mnist is probably going to be lower. It's definitely lower, not just probably. I should have put only 20. Any other questions, guys? I know there is a lot of details to remember. So please, if you have time, or I would really recommend you to have a look again at what we did previously and try to train these neural networks by yourself. Try different architectures.
Reda?
Yes?
Yes, sorry. I just have also problem with preparing data because I have a corpus of images. So for preparing this data to be included in this model or other architecture of CNN, it's me crazy. I don't know how.
I will show you an easy example after this one. I hope we will have time. I will show you there is a very easy way to load your data, to transform them, to use transfer learning, but this is after this example.
Okay, thanks.
Guys, whilst we are waiting, do you want to have a pause, quick pause, 10 minutes one?
Yeah, can do.
Yeah, let's have a 10 minutes pause and we come back.
Nice.
Okay, thank you.
Thank you.
Thanks.
This conference will now be recorded.
So as you can see, we finished the training and we are at an accuracy level of 99.5 here. And accuracy on training, so on testing is 99.5, and here it's 99.76 because the loss is decreasing. So the accuracy on training is increasing. So you can, Emil, you can see now it overtook this.
Yes.
Now it's better because the more we are optimizing, but this is increasing just slightly, and it fluctuates sometimes. So it's not as stable as this, but it is not bad. You can see here with this model and add in some dropout, we got 99.53%, and before we got the best one was 98.71. Let's try now. So this is the model summary. We discussed it. These are numbers. What's this number? Can you read it?
3.
And this one? What is this?
1.
Yeah.
0.
Yeah, I just want to make sure that it is readable, that's all. And this?
Yeah, it's okay.
7.
7. So these are prepared so I don't have to draw them. So they are just represented in a matrix format. So an image is just a bunch of pixels. So it's 28 by 28. And I convert them to reshape. I just add a third dimension with 1, like I did before. And I incorporate it. So here we are predicting with the first sample 1. Let's see if it can predict it as 3. Sample 1. Is it going to do it or? Yeah, 3. Got it. And even it was drawn like a bit down. So now let's try 1, sample 2. 1 again. And sample 3. 7 again. It does well. What do you think?
Yeah.
It is fine, yeah. You can even like slide it here, put the 7 here or here, and it should be able to do it because it's convolving. So this is the first example about mnist. Most probably courses when they start with this dataset because it's so simple. mnist. Let's go now. Well, I have to restart the kernel here because this model is inside here in the GPU. I can't have a second model in the same GPU. It will be impossible. So if I call restart to make it a simple way, I will remove everything that is in this kernel. And now let's go for fashion mnist. This is a more complex data set, same size as you can see here. This is how a sample looks like. So we are downloading it. Let's do it again. Sometimes it doesn't show it. Now it doesn't download it because we already have it. Yes, this is the image. 60,000 samples, 10,000 for testing, 28 by 28 shape, 10 classes. Well, we have 10 types of things. So everything is the same here. I didn't explain this, but we divided it by 255 because the values are between 0 and 255 for all the colors or the grayscale. So we transform it into something float between 0 and 1. That's why we divide all the values by 255. Then we have this model. So it's 2 conv layers, max pooling. Both of them are with Rulu. Then 2 again, max pooling, flatten, a big dense, and another dense. We have 3 dense layers instead of just 2. So it's going to be probably a lot bigger. So this is, let's train it. It's going to take more time, I believe. How much epochs do we have? Let's do just a 20. Take a lot of time. So we didn't have any dropout here. Yeah, this. Here we don't have any drop. We have a dropout at the end, only one. Here.
Reda?
Yes.
Yes. What about the make one prediction? You mean for just one image, for telling which class belongs? Is that what you mean?
I didn't get what you mean. Could you
This,
repeat, please?
the last line. The last
Here?
line about the model. Make one prediction.
Yeah, here.
This is for predicting one images. One
Well,
image.
yeah, here I'm trying only one prediction. Yeah, one single image. I can try more.
Okay.
Mm-hmm. It's a bit struggling. You can see the difference between the two is higher than before, between accuracy on training and testing. But here we have 3%, about 3 or 2.5 or something. It's clear that the dataset is more complex than the previous one. Feel free to ask any question while we are waiting.
Reda.
Mm-hmm.
So what would be acceptable as accuracy, like for both testing and training?
It really depends on the problem. There is no like magic number. Generally, you tie it to the business use case, what you want to achieve from it. And then you see how much improvement you can have. For example, let's say that you have a data set where you need people to assess what it is. The image, you need people to assess them. You can either have, of course, these people, or have like a machine learning model that does it like that. And then you will see how much cost both will give you. So people mean you're going to hire some folks, and you are going to pay them. They will take some time. A machine learning model, after being trained, will be almost will take a few seconds to do the prediction after training. Training takes some time, but prediction is very fast generally. So you see, if accuracy of 100% is very important, like for the medical diagnosis or something like that, maybe it's better to go with an expert, maybe. But an expert at the same time will cost a lot of time. And on the other hand, if time or speed is very important, then you might go with this model. So it's like a trade-off between speed, accuracy. It's like a business decision, not just a simple numbers decision.
Yes, yeah.
But right now, like some machine learning models, in certain cases, they are even beating experts.
This is quite scary.
Not overall the time, but for example, in images like experts were beaten like a few years ago. Models like that can do better than experts, like even for medical diagnosis from images. I have today an example about that, about some chest scans.
One day we will be all jobless. We will just rely on models.
It's possible. But we will change. We'll find something else. That's how it goes.
Yeah, I checked the CAPTCHA thing that I said this the last time. Yes, they are using us.
There is some articles written about them.
Yes, yeah. If you just Google it, yeah. If you just put like is CAPTCHA like using us to train the model? Great. Yeah.
I'm impressed with your instinct.
Yes.
That's great. You figured them out before even looking.
Yeah.
So this is the last iteration, and we are at 92.6, which is not bad. But you can see that the thing on training is very high, almost 100%, 99.30. The difference is like 8%, which is a lot.
Yeah, is it acceptable? Sorry, Reda, to have like accuracy.
It's okay. You can see that from here, the testing was not improving. 92, like from here, from iteration number 6 onward. You can see from number 6 we had 92.5 and 95%, or sorry, we had 92% here and 94% here. And from here, the improvement on testing was very small, but on training, it's going higher. You can see that.
Yeah.
So this is not really improving a lot. So from this point, we can say that we start to overfit. We are not losing a lot. We are not losing here, but this percentage, this extra bit, is probably just overfitting. It won't translate well in real life. This from 94 to 98 or 99, 5 extra percent may not translate well in real life. Now let's have a look at another model. It's basically the same one. Again, 64 filters per in the top 2 layers, max pooling, dropout, a little bit of dropout here to remove some features. Then, like I said, the more we go in depth, the more filters we have, because complex shapes have more variations than basic shapes. So here we have just 64 basic shapes. But if we go here to the complex ones, we are going to have more, because the number of combinations goes higher, it's exponential. And then I added a dropout here again. Here I think I had only one dropout, only this one. But here we have a couple of dropouts. And another one after the 2 max pooling. So a little bit of dropout here. 50 is a lot. Let's just try 20, because I think the more dropout you add, the better. It's better to add more epochs. But that's fine. We can't wait for 50. You can see the difference when we added these dropouts. So here we are in the beginning, 76%. Here in the beginning, we were at 82 on training. So the dropout got reduced on training. That's the effect. There will be like a closer gap. This will be reduced and this will be higher. The difference between the two will be smaller.
Reda, more the accuracy of test. Reda, hello?
Yes, I can hear you, yeah.
Okay. More the accuracy of test is close to accuracy of training, so the model is good.
Yeah, it is better to have it that way. It means the model is probably not overfitted. If the difference between the two is too high, the model is probably overfitting and can't do well in real life. We try always to have them as close as possible.
So we can keep it the same model, but adding or maybe removing some layers.
Of course, you can remove some layers. Yeah, you can remove some layers. Yeah, or add more layers. Yeah, and you can even keep the weight and add, and that's what we call transfer learning. That's the next part.
Okay.
So you can see here,
Thanks.
This is not improving a lot like before. Iteration 7, and we are still better here on testing. You can see the effect of dropout and how it regularized things. It's preventing this from going high at the expense of this.
Reda,
Uh-huh.
I have a question, but can you please scroll up to the yeah. Yes, no, just in here, second model. Yeah, thank you. So when we just do a dropout of 0.5, so we take in 50% randomly, right?
Exactly.
And then we create in multiple neuron networks from it.
And then when it's the same one, is just we are taking out some neurons randomly out at each iteration.
Yes. And then in the second dropout is another 50%. So is it
for that layer. 50? It applies only to the layer before it. It's not to. It doesn't apply to the whole network. So it applies only to this.
Oh, okay.
Well, this is a max. Well, sorry, it applies to this actually.
Yeah.
The max pooling, but this is basically based on this one. So it applies only to the. If you want to have a dropout at every layer, you have to put after each layer the dropout. Okay.
Yes. Okay. So this is for this dropout. For the second one, just underneath. Yeah.
Uh-huh.
So is it we take another 50% of the whole
Of this. Only
okay.
of this layer. It applies only to the layer before it.
Before, okay.
Yeah, it can inhibit some outputs and deactivate the neuron from learning. Okay, and same here.
Yeah.
This will be applied only to this.
Okay, yeah.
Is applied to this. We can't, of course, this is silly. If we apply a dropout to the last layer, it just doesn't make any sense.
Yeah.
Yeah. We don't want to remove certain outputs. That doesn't make any sense.
Yeah.
Yeah. So we don't put a dropout here. We have to keep all the outputs.
Okay, thank you.
You can see, guys, how this is like improving, and this is improving very little, not at the expense of this. It's like it doesn't. The dropout is preventing the network from learning things that are not meaningful. That doesn't generalize things that are not general. You can see this is like improving just a little bit, and this is also improving. So here we have 93%, which we couldn't get in here. Here we plateaued at 92 point something, and this went very high. But with the dropout here, it's very interesting. This is not exploding at the expense of this. 94, 93 here. Slightly more, but it's not going crazy like in the previous case.
Yeah, and Rida, is it our aim is not to get the accuracy, the training accuracy high, is just getting them like closer. Is that correct?
Closer and as high as possible, yes.
Yes, yeah.
Yeah.
So like between like having training accuracy of 99% and testing accuracy of 90%, and for example 95 we would prefer 95 for both rather than having 9. Yeah,
Definitely.
Okay.
We prefer 95 for both rather than 190% and the other 99.
Yeah, okay.
It's a lot better, because when we present accuracy, we always present it on testing, not on training. So 93.7. I think my best score here was 95%, if I'm not wrong. If I add more epochs, I think with 50 I reached 95% here, which I wasn't able to reach by then. But you can see here it's super close, not even 1% difference between the two. You can see how the dropout is affecting things. It doesn't letting this go high in accuracy for meaningless reasons. It acts as a very good regularizer. So yeah, we got like almost 94% with 20 epochs. So that's, you can see the dropout is very interesting in this like averaging. It's good that we get very high accuracy, but at the expense of the testing accuracy, it's not that good. And with the dropout, we are just creating the effect of training multiple neural networks. Same goes in here. Dropout is a little bit, 25%. That's a little bit of dropout. We are ignoring like randomly by chance of 25%. Randomly here. When here it's at the feature level, we are like ignoring some features. And same here, we are ignoring some features. Well, once you feel familiar, we can go even deeply into what this means. I don't want to like give you this extra information that can like make things more complex or more confusing. But this is the main intake. Are you happy, guys, with this session? Shall we stop, or I had like another topic I wanted to talk about, but I think it will be too much. I think we should stop for today. What do you think? We had even Maria leaving. Few guys also left. Let's stop here.
Nice.
Okay, next time we will do transfer learning, and we are going to see how we can train a model and taking advantage of a layer that was already trained in here. A very complex layer that was already trained by other people, and we can reuse it without a lot of efforts. So thank you, guys. Have a nice week, and see you next time, inshallah.
Thank you, Rida.
Thank you, Rida.
Many thanks.
Thank you.